Hello everyone, welcome back to chapter 23. In the last video we saw a number of different examples of Gauss's law, how to apply Gauss's law to different geometric distributions of charge, and then use that to produce the electric field expression. And what we saw was that given the proper setup of Gauss's law, it's actually quite a bit quicker and more efficient than a lot of the calculus approaches. And so we want to continue using Gauss's law as much as we can for these symmetric systems where we can take advantage of that nice geometry, and we'll leave the calculus approaches to the not so nice geometry. But as we move forward, in the previous video we had a number of examples where we looked at conducting and insulating materials that were used to form either solid or hollow spheres. And we saw that as long as we had uniform charge distribution about our sphere, and as long as we were outside of that sphere, even if we were right up on the surface of the sphere, as long as we were outside that sphere somewhere, as long as our radial measure was greater than or equal to the radius of the sphere, then that sphere would act like a point charge. And we could use the expression of Q over R squared to describe the electric field. And that would work for all four of these case scenarios. Again, because our uniform charge distribution would basically allow us to use the center of charge analogy, which would get us right back to this expression again. So our center of charge analogy would assume that all the charge of the sphere collapses down to a single point at the center of the sphere, and then we treat the sphere like a point. But now we can also see that Gauss's law supports that same idea. All right, well, everything that we've done so far has been outside of the sphere. So now we want to see what happens if we go inside of a sphere. And again, we're going to consider all the different combinations, whether we have a solid or a hollow shell, if it's made of conducting material or insulating material. But for all four of these combinations, we still want to work with uniform charge distribution. And we'll start with the solid conductor. So we have a solid sphere made of some conducting material. And just like in previous examples, once we put some charge on this sphere, it will automatically begin to distribute itself until we achieve this uniform charge distribution. And we know that as long as we are outside of the sphere, it will act like a point charge. But now we're going to go inside the sphere somewhere, maybe right there. And we'll say that this location has a radial value of A. So the value that we're measuring is less than the full radius of the sphere. So R is now equal to A. And what we want to do is we want to apply Gauss's law to this situation to see if we can measure the electric field at the radial position of A. But keep in mind that there are plenty of other positions within that sphere that exist at a radius of A. And so what we have done in mapping that out is we have basically drawn ourselves a Gaussian surface. If we apply Gauss's law to this system, Gauss's law says we have to relate enclosed charge to the electric flux that passes through that surface. Now there's two ways to go about this. We can try figuring out what the electric flux expression is going to provide, but all of our charges are currently outside of our container. In other words, our Gaussian surface is not containing any charge. We have zero charge inside of our container there. And so what we can do at this point is we can say, well, epsilon naught is a constant. We could factor that out of both sides, and this means that the net flux that passes through the surface area of our container has to be zero. And the reason that this is true, let's take another sphere down here, and we'll have a charge over here somewhere. Now this charge is going to be sending electric field lines out in all directions, and so we can see some of those field lines are passing through the surface of our sphere. But as these field lines enter the sphere, keep in mind that at some point later they exit the sphere. So what enters the sphere eventually exits the sphere, and we get a net concentration of zero for the flux. Now the reason that we did not get zero flux in some of the previous examples, so when we had the charged sphere of any kind of material, it didn't matter. If we put our Gaussian container outside of that sphere, well, now we're containing charge. And why doesn't this want to change color? Here we go. And so now we have electric fields that are passing through the surface, but if you notice, all of those electric fields only exit. They're only traveling in the outward direction. If we had electric field lines that were traveling in, well, that would be a different orientation for the flux, and we could add those together and call that zero. But that's not what's happening with that contained charge situation. Down here, I have no charge contained within my Gaussian surface, and so even though we could go through a very long, drawn-out discussion as to why all of the flux through this surface would add up to zero, it's so much easier to just follow along with the math in Gauss's law that says if you don't have any charge contained within your Gaussian surface, then the net flux has to be 0. If the net flux is 0, there's only 2 ways that could happen. Either you would have to have an electric field that's 0, or you would have to have a surface area that is 0. And with the radius of A that we're using for our Gaussian surface, that total surface area is not 0. So the only thing that's left is for the electric field to be 0. And so now we have our answer. The electric field magnitude inside of our uniformly charged solid conducting sphere is 0. And that's because we did not enclose any charge. All of the charge is sitting at the surface of the physical sphere. All right, well, let's move to an insulating solid. Actually, let's save that for last. Yeah. Let's move down to the conducting shell. And we'll start over with our picture here. I'll go ahead and leave Gauss's law there because we're going to need to use it again. So we have our conducting shell of radius r, but because it's a shell, we've got a very thin shell where all of our charge can exist, and then everything else inside of this shell is empty space, it's hollow. And once again, I'll ask, what is the electric field at a radius of A from the center of this sphere? Well, as far as Gauss's law is concerned, this picture is no different from the solid conductor, because the moment I try to enclose the region that is bound by the radius of A, there's no charge there. And if there's no charge to enclose, then the electric field is going to be 0 once again. So now we can see that the electric field inside of our conducting shell is also going to be 0. And it doesn't matter where we look inside of these spheres. I can look right here, I can look right here, I can even look right at the center. But any of those points inside of the sphere, if there is no charge present that I can collect inside of my Gaussian surface, I'm not going to have any electric field present at that location. Alright, so now we'll move on to the insulating shell. And for the insulating shell, if we remember, we said we had a little extra work that we would need to do in order to achieve that uniform charge distribution. We'd have to get out a rag or something and polish the surface of the sphere until we get all the charge to distribute, but we'll assume that we're already there. And so now the picture that we have for the insulating shell of uniform charge density is really no different from that of the conducting shell. And I pose the question once again, what will the electric field at radius A be inside of this insulating shell? And once again, Gauss's law says it's 0 because there's no charge there to be enclosed. Okay, so it's looking like we've got a pattern going on here. We said that whenever we were outside any of these types of charged spheres, as long as they were uniform in their charge distribution, then they would all act like a point charge. And so now it's starting to look like as long as we go inside any of these, we don't get a field. Until we get to this situation, the insulating solid. The insulating solid, we are going to magically figure out a way to distribute charge all the way through the volume of our sphere. So we still have uniform charge distribution. But now if I try to measure the electric field at some point a distance of A from the center of the sphere, we will see that we do in fact contain some charge. And because we've contained some charge, we will have some net amount of electric flux passing through the surface of that Gaussian surface that we've drawn here. Okay, well, everything outside of that container is basically not going to contribute to the problem. And we've seen that with the other three case scenarios. If I did not have charge inside of my Gaussian surface, then it does not contribute. It has to be contained. And so what we could do to kind of make our lives easier is we could say, well, if all of this charge outside of our container doesn't contribute, why don't we just get rid of it? And so basically you just have a smaller sphere with some charge inside of it, and now you're looking for the electric field at the surface of that sphere, and we already know how to do that. We know that this sphere will act like a point charge once we sit at the surface. The problem is that the enclosed charge that we have to work with is no longer the total charge that the sphere was holding. There's some smaller amount of charge inside of our Gaussian surface here. So I'm gonna backtrack a little bit in our work. I'm gonna go back to the picture that we had of the solid sphere. There we go. I need to figure out how much charge is actually being enclosed. Oops. Switch over to the highlighter here. I need to know how much charge has been enclosed inside of just this region, and then I can plug that into our Gauss's law expression and solve for the electric field. So here we go. Back to our uniform charge distribution. This is going to be what saves us. We have for the total sphere, can't spell, SPH. So for the total sphere, we have a total amount of charge Q, which has been uniformly distributed about the total volume of the sphere. And so that total charge has been distributed about the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. In our case, the total sphere has a total radius of big R. And this is what we call our volume charge density. And we give that the name of rho. So if you remember in the previous chapter, we had a linear charge density of lambda, and that was charge per unit length. We had a surface charge density, sigma. That was charge per unit area. Now we have a volume charge density of rho. And because our charge distribution has to be uniform, it should not matter what the sample size of charge is. And that means that if we look at just the enclosed portion of charge and compare that to the volume that we are enclosing, so this is the highlighted section at radius A. That enclosed charge compared to the enclosed volume at radius A, that has to equal the same charge density. And so these two expressions have to be equal to each other. And this is how we're going to find out how much enclosed charge we have inside of our Gaussian surface. So we'll go ahead and set those two expressions equal. Q total over 4/3 pi big R cubed has to equal charge enclosed over 4/3 pi A cubed. The 4/3 will cancel out, and we're left with the ratio of charges to cubed radial measures, and so our enclosed charge turns out to be the total charge times the ratio of A cubed to R cubed. And if you want, you can combine those cubed terms, A over R cubed. Well, now that we know what our enclosed charge is, we can bring that up to Gauss's law. We can plug that into Gauss's law. I'm actually going to use this version just because I've done this derivation before, and we're gonna eventually introduce an area expression for our container, which is also going to have some values of little a in it, and I'd like to be able to cancel some of those out. So Gauss's law says enclosed charge, which we now have, is Q total A cubed R cubed epsilon naught E dot dA. And now is where we're going to make that assumption that anything that is not inside our container is not going to contribute. And so we basically just have a charged sphere, and now we're trying to measure the field at the surface of that charged sphere of radius A. We've already done this problem before. We've already solved for the electric field at the surface, and it is the point charge expression right here. The only thing that we need to do is we need to update the values of the charge and the radius that we're sitting at. Well, the charge that we're using, that's right here. And the radius we're using is A, so that's taken care of. But if we continue through the math of Gauss's law, you'll remember that our previous arguments state that the electric field at any radius of A should be uniform. So our electric field can come out of the integration process after we take care of the dot product. But again, we've already been through this example before. The dot product is going to result in a cosine zero relationship between our electric field vector and our area vector. So that just reduces to a 1. And so we have epsilon naught E integral dA. So dA is the area of the container that we're using, and our container is a sphere of radius A. So surface area of a sphere, 4 pi A squared, equal to Q total A cubed over R cubed. So here's where those A values are going to reduce. And now that we're done with all of the integration, we can rearrange everything to solve for the electric field at point A. So to do that, we will need to divide both sides by 4 pi epsilon naught, which is our K value. We have Q total A over R cubed. We have 1 over 4 pi epsilon naught. And there we have it. There is the electric field inside of a uniformly charged insulating sphere. Now, one thing that we should note is if we do in fact have this uniformly charged sphere with charge all the way through its volume, what happens if I try to measure the electric field right at the center of this sphere? So in that case, A is now equal to 0. Well, if I let A go to 0, I can see in the expression the whole thing will collapse to 0. And that is because at the center of this sphere, all of our electric fields are going to be pointing right towards the center of the sphere from all directions. Those field lines are vectors, and so when they all add together, we're going to get 0. But it's a lot easier to just let Gauss's law tell us that with the math by letting A equal 0. Another thing we can try is what would the electric field at the surface of this sphere be? And, well, we already know that. It should be the point charge expression. We know that anytime we step outside of the sphere, that it's going to act like a point charge. I call this Q total because we would technically be enclosing the total charge of this sphere. But let's see what happens when we let A equal R. If we do that, we get R over R cubed, which is R squared, and yep, that's exactly what we get. We're back to the point charge. And this is an important outcome because whenever we have any kind of expression that is supposed to describe what is happening in the system, basically we're trying to measure the electric field right here at the surface of the sphere. Well, it shouldn't matter if we approach that point from the inside of the sphere or if we approach that point from the outside of the sphere. When we get to that point, we should be measuring the same magnitude of electric field. And so it's important that both of our methods, whether we're using Gauss's law on the outside of the sphere or Gauss's law on the inside of the sphere, that both of those expressions converge to give us the same value. So that's kind of similar to the process of setting up and taking limits in calculus from different directions. Sometimes you'll take a limit from the positive. Other times you'll take a limit from the negative, and if you're not getting the same outcome, then that tells you something about the differentiability of the function. But I'll leave that discussion to the calc professors. All right. So it looks like out of all 4 of these case scenarios, the first 3, the ones that were highlighted, all end up with an electric field magnitude of 0. And that's because in those first 3, we did not have any charge that could be enclosed. But with the insulating solid, we were able to enclose some charge. And so we were able to get an electric field. And now we have an expression that shows us what that is going to be. So now that we've seen what happens with a charged sphere and how a charged sphere is going to behave both outside and inside of the sphere, can we take that idea and apply it to something like a charged cylinder? Well, once again, we're going to have to consider what is the cylinder made of? Is it a conducting material? Is it an insulating material? Is it solid? Or is it hollow? So is it a shell? So we could have a solid conducting cylinder, a solid conducting shell, a solid insulator, an insulating shell. But in all of these case scenarios, let's put in a central axis through our cylinder here so that we can measure the radius of our cylinder. And then, well, we can just progress through all of the different case scenarios that we have here. And we'll start by trying to measure the electric field at a point that is outside of the cylinder. And I'm actually going to redraw this. Oops. I'm erasing things that I don't want to erase. We'll redraw the cylinder. I want to draw this in a more horizontal axes. So there's our cylinder. Here's our central axes. Here's our radius of R. And we'd like to know what the electric field is at some point outside of the cylinder. And we'll go ahead and call that little r. So we have little r bigger than big R. We'll start with the first case scenario of a solid conductor. Now, if I have a solid conductor, the moment I put charge on this solid conductor, that charge is going to distribute itself uniformly about the surface of the cylinder. And we'll go ahead and let that point in space be above the midpoint of the cylinder. And about now, we should be asking ourselves, well, this looks really similar to the line of charge. Can we assume the cylinder to be like a line of charge? And my answer would be, well, if you start to get really far away from the cylinder, then yes, it would start to look like a line. But let's see what Gauss's law says. Gauss's law says if we were to take this cylinder and extend it out infinitely long in all directions, then every point at a distance of r would be the midpoint. And we should expect to see the same magnitude of electric field at every one of those points at a distance of little r. And so along that line, we're expecting uniform electric field, but we should see that same uniform electric field at any radius of little r. And there is a shape in the form of another cylinder that exists at the radius of little r. And now Gauss's law is pretty much going to reproduce exactly what we had for the line of charge discussion. Because now we can see that for every charge along the cylinder, those charges are going to be sending their field lines up to point P. Those field lines are going to add and cancel out their horizontal components, leaving only vertical components of field. That means that for every field component, I'm going to backtrack here a little bit. That means that for every field component that passes through the surface of our Gaussian surface, so that's what we have here, every field vector that passes through every infinitesimal piece of area is parallel. So our dot product, which is hiding a cosine, theta between those vectors is 0, cosine of 0 becomes a 1. We now have charge enclosed equals epsilon naught EdA. We're expecting the electric field to be uniform at all points along the surface of our cylinder, or our Gaussian surface cylinder, I should say. So E can come outside of the integral, and then we're just left with taking the integral. And just like the line charge expression, the only place where we're really concerned about the electric field is up here along the drum portion of the cylinder. We're not concerned with what's happening along these end caps. And so the only area that we're going to use is the area of that drum portion. So again, this is something that we've already done with the line charge. We know that the area for the drum of the cylinder is pi r squared L, where L is the length of the cylinder. So now is where we'll tone this down back to a finite case. We're done with the calculus part, which, you know, there really wasn't any calculus involved. We just had to look up the area of our container. And now we rearrange to solve for E. Charge enclosed is just going to be the total charge on the cylinder divided by our epsilon naught pi r squared L. Let's see, did I get it? Oh wait, I made a major boo-boo in here, didn't I? That is not the right value. That is the area of one of the end caps. I need the area of the drum portion, which is the perimeter, 2 pi r times L. 2 pi r times L. There we go. That's much better. Well, that's exactly the same expression that we got for the line of charge. So our cylinder of, I should have put this up at the beginning, but we're always going to assume this to be true, uniform charge density, until we're told otherwise. But for our solid cylinder of uniform charge density, as long as we're outside of that cylinder is going to act like a line charge. And so now we can go through some of the other case scenarios, making the appropriate changes where we need to. Let's consider a conducting shell. Well, for a conducting shell, this would just mean that there would have to be a hollow portion of this cylinder. But that doesn't change the fact that all of the charge still needs to spread itself out over the surface of this conducting material. And so once I go back up to this point P, everything that we've done through Gauss's law is going to be exactly the same. And so for a conducting shell, if we're outside of that conducting shell, that charged cylinder will act like a line charge. So now we switch over to the insulating shell. For the insulating shell, we would have a little bit of work to do in actually achieving that uniform charge distribution. So we'd probably have to take out a rag and polish the cylinder, move that charge around. But once we achieve that uniform charge distribution, the picture in terms of Gauss's law is no different than the previous two. And so the math is going to end up with the same solution. If we're outside of the uniformly charged insulating shell, it will act like another line charge, until we get to this situation right here. So now we have to consider what's going to happen if we have an insulating solid and we were able to achieve some uniform distribution of charge throughout the volume of that cylinder. Well, Gauss's law says you're still enclosing everything. You're still enclosing all of that charge, even though it's distributed throughout the volume of that cylinder. You still enclosed it all. So Gauss's law brings us right back to the same result. Just like with the sphere. Didn't really matter what kind of sphere we had, whether it was conducting or insulating or a solid or a shell, as long as we had uniform charge distribution and we were outside of the sphere, it acted like a point charge. Now we're seeing that regardless of what our cylinder is made of or how it's constructed, as long as we're outside of it and it has uniform charge distribution, it's going to act like a line charge. Of course, the next logical step would be to go inside of the cylinder. So we'll draw this cylinder a little bit bigger. And we have the full radius of the cylinder. We'll go back to the solid insulating conductor shell combinations. What we're going to see next is very, very, very similar to what we saw when we went inside of the charged spheres. If we start with a solid conducting cylinder, all of our charge will distribute itself about the surface of the cylinder. And now we want to measure the electric field at some radius of A inside of the cylinder. Well, just like before with the sphere, we're going to map out a surface that exists at every radial value of A. But if we do that, all we do is we produce another cylinder. This is now our Gaussian surface. This is the container that we want to use to help us in evaluating Gauss's law. But right away we should be focusing in on this aspect because there is no charge inside of that Gaussian surface. All of the charge is at the surface of the physical cylinder. And because there's nothing to enclose, the electric field inside of our solid conducting cylinder is 0. If we switch to a conducting shell, okay, well we'll make the shell. We want this cylinder to have a very thin shell. And we'll ask the same question. What is the electric field at radius A? Well, our Gaussian surface at radius A still is not enclosing any charge. And so the electric field at radius A will be 0. For an insulating shell, so we've still got the same hollow cylinder picture. We've somehow uniformly distributed charge about the surface of the cylinder, and now we try to measure the electric field at radius A inside of that hollow cylinder. But again, there is no charge inside of our Gaussian surface. And with no charge, that means no electric field inside the cylinder. The one thing that's going to change is if we try to enter a uniformly charged insulating solid. So like the solid insulating sphere, we can now have some charge uniformly distributed about the volume of our cylinder, and that means when we draw our Gaussian surface, we do contain some of the charge of the total cylinder. But we can take exactly what we did with the solid insulating sphere, and we can use that as sort of a template in helping us find the electric field inside of this solid insulating cylinder. Once again, the total charge of the cylinder compared to the total volume of the cylinder has to have the same ratio as the enclosed portions. So this is our uniform charge density, aka the volume charge density. And so we can get the enclosed charge just by looking at those ratios. We would have Q total times the ratio of the enclosed volume to the total volume. And so we need to figure out what is the volume of a cylinder going to be. Well, in that case, the volume of a cylinder is pi r squared L. So we take the area of the end cap, which is pi r squared, and then we multiply that by the length of the cylinder, which we will call L. So the enclosed volume will be the volume produced by the radius of A. The total volume will be the volume produced by the radius of big R. And in this case, we see the pi's and the L's cancel out, and so we're left with a ratio of the radius values similar to what we had with the sphere. But now this enclosed charge can go back into our Gauss's law expression. We have an enclosed charge of Q total. Whoops, sorry, that should not be a cube, that's a square. Square equals epsilon EdA. Alright, here's where our job gets easier. Remember when we said with the sphere, any of the charge that is outside of our Gaussian surface does not contribute. And so all these charge values that are currently outside of our Gaussian surface, they're not going to contribute to the math. And so basically all we have left is a solid cylinder of radius A, and we're trying to find the electric field at the surface of that cylinder. Well, we've already done that example. We already know that if we're at the surface of a charged cylinder, technically we're just barely outside of it. Well, how is it going to behave? It's going to behave like a line charge. The only difference now is that we have to update the charge value and the radius value. The charge value is the enclosed charge that we're using right here. And if we carry through the math with Gauss's law, the integral that we take with respect to the surface area of our Gaussian surface, or our container, is a surface area of radius A, which is 2 pi A times L. This is the surface area of the drum portion of the cylinder. And we have Q total, A squared, R squared. We rearrange for E, we get Q total. We're going to lose an A on either side. And what we're left with here, let's see, we have 2 pi epsilon R squared L. We still have an A in the top there. So that is the electric field inside of our uniformly charged insulating cylinder. And just like with the sphere, we want to play the what if game. So what if we try to measure the electric field at the very center of the cylinder? I'll come back down here and redraw our cylinder. So we've got all these charges inside our cylinder. So what's going to happen if we try to measure our electric field right at the center of the cylinder where A is equal to 0? Well, in that case, the electric field expression reduces to 0, but at the same time we should realize that all the electric fields that are going to be produced by all of these charges, when they get together at the center of that cylinder, they're going to cancel out due to the vector orientations. And the next thing we would try is, well, what happens if A equals R? So what happens if we go back to the surface of the entire cylinder? So what if we consider the entire charge of the cylinder? Well, so now we're technically back to the surface of the cylinder. In all of our previous discussions, we said that once we get to the surface of the cylinder, it should start acting like a line charge. But if we replace A with R, we lose an R, and what's left? Q total 2 pi epsilon RL. Well, that is the line charge expression. All right, so that concludes this particular video when it comes to using Gauss's law. Not only were we able to reproduce a lot of the things that we already knew about the spheres acting like point charges, but now we can see that as long as we're outside of a uniformly charged cylinder, it will act like a line charge. But now we can use Gauss's law to go inside any of these constructs, and given what the material is made of and whether it's solid or a shell, we can then use Gauss's law to tell us what the electric field inside of these shapes is going to be. And so in the next video, we're going to depart a little bit from the way that we've been using Gauss's law. We have almost exclusively been using Gauss's law to help us derive the electric field for a given system, knowing what the charge is. So if we can take our knowledge of electric charge and use that to solve for the electric field in the system, can we go backwards and use our knowledge of the electric field to tell us how much charge is present? So that's what we're gonna try in the next video. So we'll see you then.